I believe many design and analysis methods commonly used in industry contain three major sources of error. In the variability handling approach, each of them is improved through three separate steps. The third improvement is the use of distribution-based evaluation indices. In conventional design and analysis, performance or reliability is usually judged by comparing single numerical values such as whether the result exceeds a target or has enough margin. In the variability handling approach, those judgments are made probabilistically by evaluating relationships between distributions. For that purpose, I prepared for different evaluation indices. Distribution comparison evaluates the relationship between two distributions. For example, one distribution may represent actual performance or operating frequency, while another represents required capability or durability. By comparing them, we can calculate the probability that performance exceeds the target, or the probability that it falls below it. This allows strict evaluation of failure probability, reliability, and performance in systems with variability. Distribution proximity calculates the probability that two-position distributions come within a specified distance. For example, in simulations, if we calculate the distribution of closest approach distance, we can rigorously estimate the probability of collision or avoidance. Distribution equilibrium can simulate market behavior. Demand distributions are calculated from consumer purchasing ability, while supply distributions are calculated from producer capability, such as production cost and investment. By accumulating these distributions in opposite directions and finding their intersection point, we can estimate equilibrium price and sales volume. These evaluation indices make it possible to rigorously analyze systems with variability and achieve more accurate design and analysis. As explained in Part 1, the variability handling approach first generates distributions that closely reproduce the real shape of actual data. Then, as explained in Part 2, it uses distribution-based calculations to rigorously obtain the resulting distributions of models and systems. Finally, in the third step explained earlier, relationships between those distributions are evaluated probabilistically using distribution-based indices. By combining these three steps, we can make much more accurate decisions in many kinds of design and analysis. At the same time, this approach also opens up many new possibilities for advanced calculations and analysis methods.